So as we've seen, one of the key ingredients of a Bayesian estimator is the prior density. For this, we're going to talk about what is the prior density and how can we obtain such a prior density. So we'll start off with some basic definitions. First, what is an estimator? An estimator is, roughly speaking, a function that uses the realization of random variables, and we use it to infer some information about a certain parameter that is of relevance to us. Then there are two viewpoints, generally, even more than just an estimation, and that's the frequentist and the Bayesian point of view. We'll just limit ourselves to what is really essential for this talk. And so a frequentist estimator is an estimator of a parameter that is unknown but fixed. There is one value that we do not know, but it does not change for our experiment. Here and in the following, we use some notation at x is a scalar. If we underline something, that's a vector, and we've put a tilde above it, that means that it's the true value. For a Bayesian estimator, we have an estimator for a parameter that is distributed according to a known prior that describes how our experiment behaves if we repeat it again and again and again. So the Bayesian focuses on being good in average if you repeat it again and again, and he said that he has some prior knowledge about this phenomenon, whereas the frequentist says, well, I'm just in this experiment once, I'm just care about this, what I have here, and I have no knowledge whatsoever. Now, here, bold font, we have random variables. We put a head over an estimate or a measurement. We use F for PDFs, and we put a lower index to specify which random variable we're talking about. We use bold font, caps, letters to denote matrices. So I've briefly touched on some basic properties of the Bayesian paradigm and will now specify them very clearly. So as a Bayesian, we say we already have a certain knowledge about the parameters that we wish to estimate. And if we repeat the experiment, that true parameter will vary according to the prior distribution. So we really have some knowledge here that has implications if we do this entire experiment infinite number of times. And we have this knowledge before we even have any measurement. What we do not know is which is the actual parameter in a specific run. Therefore, we need measurements to get more precise information about that parameter. So more precise can, for example, mean that we get a density with lower variance. So what frequentists sometimes say about Bayesian philosophy is that there is no way to know the prior density. So how do we actually generate one in practice? For this, I want to do an exercise here. In practical settings, I would obviously discuss with you your suggestions. So in this case, I will read it out and you will pause the video afterwards. So assume you're working in quality control of a tile factory. There are contract penalties, and to avoid these contract penalties, the management wants to know the average length, and they also want to know how certain you are about this. So from your experience, you already know that the length of a batch is normally distributed, and you know the standard deviation. So it's a simple case that we even know the standard deviation. So you try to tackle this in a Bayesian way because you're a Bayesian, and you have some hunch that there are 5 inches long on average. Now, try to get to a way how you would give this prior density to the management, and pause the video here. We will get to the solution in the next slide. As I said, we know it's normally distributed and we have a known standard deviation. So what we do need now is the mu parameter of that normal distribution. So you can do the subjective Bayesian. Maybe some of you have chosen this way, the subjective Bayesian. You just set mu to 5 inches and you set a higher standard deviation than the known one to make up for it. However, the caveat is that your certainty will be off. You've just increased it very much, and you will have a bias towards 5 inches. Maybe some others of you have chosen the empirical Bayes way. You've taken a small part of the batch and you calculate your mu parameter accordingly. Just for that part, you say that this applies to all of them. Well, obviously your certainty will also be off and it will be biased towards the mean of just that part. And another thing that, strictly speaking, you're using some measurements of that are not used in a strictly Bayesian way. So the robust Bayes solutions, maybe not many of you have chosen to go that way, but there you just take a set of prior distributions, say that the mu is somewhere in between 5 and 6 inches, and you work with all of these. Then you have an entire set of these prior distributions. Here, that is your mu value, that is 4 to 6 inches here, and this is your stochastic uncertainty, of which you know the sigma parameter. What you can do is you can say that based on the measurements you've gotten, you can say the mean is between 4.7 and 4.8 inches with some credibility. You can get these posterior sigma values of your posterior densities, which help you provide valid credible region. So you have to be cautious. If we say that we have such a credible region, then you would have multiple credible regions for all of these elements, for all of these prior densities. So you would be conservative in a way that you would say that you would never state that you know more than you do, but you will have some additional imprecision in your statements. So we've just talked about the robust Bayes approach, in which you can choose whole sets of prior distributions. Now think about it as an exercise. How does this approach relate to the frequentist and Bayesian approaches? Think about the assumptions you have about these parameters that you want to estimate. How are they distributed? Distributed may be a Bayesian thing, but just think about this. Just pause the video here and continue once you have some idea. So actually, it's a generalization of both the frequentist and the Bayesian point of view. Because if you take the frequentist point of view and you really want to specify a prior distribution, then it would be that this is just one point which you do not know. And you have a whole set of these prior densities that cover the whole state space. This way, you're agnostic to the true value and you say that there is just this true value. There's no repetition of experience. There's just this one true value. And by saying that all of these elements of the state space can be that value, you can have this direct distribution that just say that this is the one value. In the purely Bayesian point of view, you have just one prior distribution. So there is just one, whereas in the frequentist you have infinitely many without any stochastic uncertainty. This is how you can interpret this.